I would love for you to join me in this. It is super fun, and no one has ever done it before in the history of celebrating circle constants, which is surprisingly short. Even if you prefer tau rather than pi as your circle constant, the next time we will get this on Tau Day is not until 2075, so you might as well still join us. If you want a short version of this and don't care to hear how it works, you can skip to close to the end, and I will tell you what you need to do. And now, let's begin. Sadly, my circumstances did not work out, and I did not get to see totality in the Great American Solar Eclipse of 2024. Then, I was doing some research, and I found out as a consolation prize that there would be a total lunar eclipse on the night of March 13th going into March 14th, 2025. I thought about this a moment and then realized, hey, that's Pi Day. And another thing, there's this person I sometimes watch, Matt Parker from Stand Up Maths, the YouTube channel, and he likes to calculate pi in various ways to celebrate Pi Day, a very sensible celebration. I thought it would be really interesting to calculate pi using the total lunar eclipse. And so that is what we are going to do. The way I figured out we can do this is using the area of an ellipse. And the reason is that the moon orbits the Earth in an ellipse. This is Johannes Kepler's first law of planetary motion. Any satellite will orbit its primary body in an ellipse with one focus containing the primary body and the other focus containing nothing. So now you know that. Here is Johannes Kepler's second law of planetary motion, which will be helpful for us. The amount of time it takes for it to sweep out this chunk of area is the same that it will take to sweep out the next chunk of area that same size. Equal areas, equal time. Got it? Okay, so if we know the area of this, and we know what fraction of the total area of the ellipse it is, then we can calculate the area of the ellipse. And the way we can do this is by approximating it. Somewhat similar to polar integration, I'd think, though I have not done it. Yes, there's going to be a bit of an arc. This is an approximation, very similar how they calculated pi in ancient times. And what we are going to do is find out what distance this is. The units will be our moon's radii, and then multiply that by the moon's radius, and we get the area of this triangle. So that's how we find out that. And next, to find out what fraction of area this is, we can measure the speed at which the moon enters Earth's shadow, probably the umbra, because that's easier to see, and divide that out of the length of a synodic month. Synodic meaning the amount of time it takes for the moon to cycle through its phases. And yes, there are other months. One notable one is the anomalistic month, and that is the amount of time it takes to go from closest to Earth to farthest to Earth, back to closest to Earth. For the next part, we need to picture an ellipse. I could slice a cone the correct way. I could stretch a circle, but I'm going to use the string and pushpin construction because that tells us where the foci are. There we go. And like I said, at one focus there is the Earth. This is very oversimplified and not to scale. And at the other focus, there is nothing. And closest to Earth is when the moon is at perigee. Farthest from Earth, the moon is at apogee. And about closer to perigee is when the lunar eclipse is. So another way to come up with the area of an ellipse is pi times half the major axis, called the semi-major axis, that's this distance here, times half the semi-minor axis, which is this distance here. Notice that this has pi included, so we can take our original area and divide it by this area, and we will get pi. So, to find out this distance, we will measure the distance to the moon at apogee, add it to the distance to the moon at perigee, and add the Earth's diameter. The original distance I told you to measure was at the time of the lunar eclipse. Also, the moon's radius will be canceled out here during the measurement, so we don't have to worry about that. Now, as for this, we can't measure it directly, but we can calculate it using the focal length, which is going to be the measurement at apogee minus the measurement at perigee. So the semi-minor axis is equal to the square root of the semi-major axis squared plus half the focal length squared, square root covering all of that. And that's how we will do it. Now the tricky part is measuring the Earth's diameter. So the way we're going to measure Earth's radius is quite similar to the way Hipparchus did it. However, he made this assumption that Earth's umbra was the same size as the Earth itself, which is false. And I'm going to show you why. So I've got this diagram. Pretend this is the sun, this is the Earth, and that's the moon. It's not to scale or anything, but you can sort of tell. And the umbra is going to follow these lines, common tangent lines between the Earth and the sun. And the other common tangent will be the penumbra. And now, here's another thing. We should be using the common tangents, but to simplify the math a bit, let's just say they pass through this point, this point, this point, and this point at the sides. And next, we're going to define some variables, which I will draw a diagram of. Again, the moon's radius will be our units. Distance to the moon, distance to the sun, Earth's radius, sun's radius, moon's radius is 1, the radius of the umbra, and the radius of the penumbra. Moreover, this point at the center of the sun will be 0, 0 on the coordinate plane, and the eclipse setup will be vertical. Let's note that the distance from here to here is the distance to the sun plus the Earth's radius. The distance from here to here, only the horizontal part, is the sun's radius minus the Earth's radius. And the distance from here to here, only the horizontal part, is the sun's radius plus the Earth's radius. We can use this information to find the slopes of these lines, and we know that these lines pass through the points distance to the sun plus Earth's radius in the y-coordinate, and in the x-coordinate they are Earth's radius and negative Earth's radius. Now we can use the slope and the distance to the moon to find out what these distances are up here. Here are the equations we get, and we can solve both of them for Earth's radius in terms of the Moon's radius and the Sun's radius. Now, these are two variables. We can then set the equations equal to each other to find the Sun's radius in terms of our Moon's radius, and then we will truly be able to find Earth's radius with units of our Moon's radius. Now here are the measurements needed to make this work. 4 of them are similar to parallax, and I'll show you how to do this. Take your finger or something else pointy and wink one eye shut so that it appears in line with one side of the object. Now wink that eye shut and open the other eye, and the goal is that it will appear at the other side of the object. Now, the distance from your finger to your eyes is to the distance between your eyes as the distance from your finger to the object is to the width of the object. You will need to do this for the moon at the lunar eclipse, at perigee, and at apogee. And also, don't forget your solar eclipse glasses, because you will need to do this for the sun right before the eclipse, as close to it as possible. Make sure that they're certified by ISO 123122 and that they have not expired. Now, if you want to take a good picture of the eclipse, you'll have to make sure that the moon is not overexposed. You may need to use a third-party camera app to do this. The pictures I have of the previous lunar eclipse last autumn, I did by zooming in very close to the moon and tricking the camera. Now, once you have these pictures, you'll need one where the edge of the umbra is visible and one where the edge of the penumbra is visible. And you can construct line segments with endpoints on the edges of the umbra and penumbra, and you need 2 for each shadow. Then you can construct the perpendicular bisectors of those line segments, and they will cross at the center of the circles, and you can use these to find the radius. Now the last thing you'll need to measure is the moon's speed. To do this, take multiple pictures to find out which way the shadows are moving, so you know which way the moon is moving. And now find 2 identifying features of the moon that are in line with the direction that it's moving, and time how much time it takes for the shadow to cross those features, and that will give you the moon's speed. Hopefully I will be able to do this, but then again there could be clouds or something could happen to me. Either way then, enjoy the eclipse.